I'm Xue Liu from Chinese Academy of Agricultural Sciences, Institute of Tobacco Research. I appreciate the opportunity to be with you today. My topic is selected atom-regulated carbon nitride for enhanced photocatalytic degradation of pesticides. My presentation is in 4 parts. First of all, let me provide something about the research background. Herbicides are the most widely used pesticides for weed control, industrial, preservative, and turf management. However, some herbicides have faced increasing criticism due to their potential adverse effects on the environment and public health. For example, even trace-level residues of colonyl ethyl in the environment could cause phytotoxicity to subsequent crop for years. Maize, wheat, and sunflowers can be affected for more than 15 months. Sugar beets, potatoes, and watermelons cannot be grown for 3 years after colonyl ethyl application. Therefore, more efficient and adaptable strategies for herbicide degradation should be developed. Photocatalytic degradation of pesticides has been achieved with semiconductor catalysts such as titanium dioxide, zinc oxide, and so on. In recent years, polymeric carbon nitride also presents great potential for pesticides degradation. Nowadays, the main drawbacks that hinder polymeric carbon nitride's application are low specific surface area and fast recombination of photoexcited electrodes and holes. Therefore, strategies such as surface engineering and element doping are adopted to enhance the photocatalytic activity of polymeric carbon nitrides. Okay, in the second part of our research, oxygen atom-regulated carbon nitride were used for herbicide degradation. Series oxygen atom-regulated carbon nitrides were synthesized via a rapid acid-assisted method. Specifically, polymeric carbon nitride was dispersed in different concentrations of nitric acid, and an ultrasound was then performed consecutively for 30 minutes. As can be seen in these figures, catalyst donated as OCN10 processes most obviously porous in the surface. Relative low concentration of nitric acid is hardly enough to alter the surface of polymeric carbon nitride, just like OCN5. Also, over-rich nitric acid may corrode the existing surface hollows and further form the coated magma-shaped bulk. Correspondingly, the BET specific surface area, pore volumes, and average pore diameters of OCN10 surpass that of the other 3 carbon nitride catalysts, which enhance the mass transfer and charge separation. The photocatalytic degradation of 10 herbicides in 5 categories of prepared carbon nitride catalysts are shown in these figures. OCN10 sample showed the highest photocatalytic activity. The OCN15 sample revealed the lowest photocatalytic activity for most of the investigated herbicides, even it possessed the narrowest band gap. For OCN15 sample, non-reductive electron and hole recombination might become dominant, which is adverse to degradation of these herbicides. Therefore, in moderate decrease in the optical gaps may lead to the decrease in the photocatalytic activities. Based on the trapping experiments, the photodegradation efficiency of all 10 herbicides were largely inhibited by the addition of potassium iodine, particularly the photodegradation behavior of amide herbicides. These 3 is almost completely suppressed. When the tetrabutanol was added into mixed reaction solution to quench hydroxyl radicals, the degradation showed a different pattern. Two investigated herbicides were not affected by the quenching of hydroxyl radicals. With the excitation of oxygen atom, the electronic structure may be tuned. Thus, we predict 4 different oxygen containing structures and calculate the band gap of carbon nitride units between the HOMO and the LUMO. The results suggested that these two structures in the units with narrower band gaps are favorably occurred after oxygen atom doping. In the third part of our research, single metal atom regulated carbon nitrides were synthesized and used for herbicide degradation. Recently, incorporating single metal atoms into polymeric carbon nitride is proven to be highly effective to improve photocatalytic activity of polymeric carbon nitrides for herbicide degradation. Because it can thanks to the optimized optical property and the facility separation of charge carriers. Therefore, we attempt to adopt this strategy to enhance photocatalytic activity of polymeric carbon nitrides for herbicide degradation. Firstly, we employed a wet impregnation approach to anchor single platinum atoms onto wholly carbon nitride nanosheets. Also, we adopted a co-pyrolysis strategy using iron-rich biomass to synthesize the single iron atom degraded carbon nitride. The presence and the ultrafine dispersion of single metal atoms on carbon nitride substrate were confirmed. You can see in these figures, no nanoparticles or clusters were observed. The detailed electronic structure and coordination information was also investigated. The peak corresponding to the metallic platinum and platinum was not observed. Instead, the mean peak at 1.62 astronome was detected, which can be assigned to the platinum-nitrogen bond. Based on the fitting results, a single platinum atom was coordinated with 4 nitrogen atoms. Also, the peak corresponding to the metallic iron and iron bond was not observed, and the iron and the nitrogen bond at 1.53 astronome was detected, and the single iron atom was coordinated with 5 or 6 nitrogen atoms, depends on the pyrolysis process. Single metal atom regulated carbon nitride exhibited significantly enhanced polymeric photocatalytic activity for herbicide degradation. Besides, it also exhibited satisfactory stability after several cycles. Moreover, the XPS was further used to investigate the chemical stability of a single metal atom regulated carbon nitride. No significant change was observed after the catalyst was used. Also, the DFT calculations for the band structure and the density of state of carbon nitride catalyst were performed based on the optimized configuration. It could be concluded that the incorporation of single metal atoms resulted in a decreased band gap compared to polymeric carbon nitrides, which was beneficial for light adsorption and the formation of electron and hole pairs. In addition, the strong electrophilic property of single metal atoms is beneficial for creating an electrodeficient environment and facilitate charge separation, oxygen absorption, and the generation of reactive oxygen species, which enhanced the photocatalytic activity. Also, the UPLC couple mass was used for the degradation products identified. The experimental and the predicted values indicated a general decline in the toxicity of herbicides to model organism after photodegradation. The toxicity effect of investigated herbicides was also evaluated by the growth of soybean seedlings. The results indicated that the phytotoxicity of herbicides towards soybean seedlings is greatly reduced after photocatalytic treatment by single metal atom regulated carbon nitride. Okay, finally, I'll give the summary of my work. Enlarged specific surface area and the moderately narrowed band gap can significantly improve the photodegradation efficiency of carbon nitride catalyst. The charge electron localization facilitate charge separation, oxygen absorption, and subsequently the generation of reactive oxygen species, which both enhance the photocatalytic oxidation. Also, we appreciate the contributions of our collaborators. Please feel free to reach out to me via email. You can find my contact information on this slide. Also, welcome everyone to visit Chinese Academy of Agricultural Sciences Institute of Tobacco Research. Okay, thanks again for listening.